Good evening. You wanted me to give an introduction to rings, ideals, and fields, so I'll start with that today. And if there is time left, we'll come back to groups. First, I'll define what a ring is. A ring, R, usually capital R is the letter we use to denote a ring, like how we use capital G for groups. A ring R is a set with two operations. So in a group, we had only one operation. For a ring, we have two operations denoted by one operation. We call it the addition. It's just notation. It doesn't have to be the addition operation. It has to be some binary operation. And the other we use multiplication. Again, it doesn't have to be multiplication in the sense of multiplication of numbers or matrices. For example, even composition, you can call it multiplication. It's simply notation. So you have two binary operations. So that's what is required. Two binary, and by binary operation, we mean that the operations are closed. So we have incorporated it, the closure property, we have incorporated into the definition of binary operation itself. If that is not the case, sometimes a binary operation does not have to be closed. You don't have to define it such that it is closed. In that case, the closure property for addition and multiplication has to be mentioned separately as one of the required properties. And we call these operations addition and multiplication. So ring R is a set with two operations, addition and multiplication, satisfying the following properties. We need the set R with operation plus to be an abelian group. Then we don't need R with multiplication to be a group at all, but we have three of the group properties. It should be commutative, associative, and should have an identity element. And for multiplication, we denote the identity element by 1. We don't need inverses. If every element also had an inverse, then R would be a group with respect to multiplication. But we, I think we define it in this way that it doesn't need an inverse for multiplication. Then these are separately with addition and multiplication. These are the properties that it should have. But if you look at integers and all, they have distributive property also. If there are three elements in the ring, then A plus B into C must be equal to A into C plus B into C. Of course, the other sided C into A plus B must be equal to C into A plus C into B. But this is taken care of by commutativity of addition and multiplication. So stating one of them is enough. So a set with two operations that have these properties is called a ring. Now there is one important thing here. This ring definition can be different in different books depending on the application. So it is possible to define this ring firstly without asking for a multiplicative identity. So if you remove this condition, that is also a type of ring. You can define a ring that way, and there is a lot of theory with rings defined in that way. The next thing is uh, you can leave out the commutative property also. So a ring can also be defined without having the commutative property for multiplication. Usually, if the ring, usually this is the most, but all the other properties are required for any type of ring that you define. This is the most basic definition for a ring. And if you include the commutative property, it is called a commutative ring. And if you include the property that it has an identity element, then it is a commutative ring with identity. But as far as we are concerned in this course, I'll only deal with commutative rings with unity. And by a ring, I mean a commutative ring with unity. Commutative ring with the identity. There can be non-commutative rings with identity also. You can include any of these conditions that it has identity or not, and you can include or exclude the commutativity of multiplication. So those type of things are also called rings in other branches and in other textbooks. Distributive, yes. Then what happens is if you have not defined multiplication to be commutative, you have to define distributive from the left and from right. So earlier I had written C into A plus B must also be equal to C into A plus C into B. That's you'll have to write that also. Yes, yes, yes. You just need two binary operations and they have to be different. Yeah, they have to be different binary operations. Can't use the same binary operation. Otherwise, it will just become a group. But as long as there are two different binary operations and they're closed, then you can use it. Even if it doesn't have, yeah, that's why I said it is just notation and these are just names. Plus and into are just notations. You can use other symbols also for the same operation. You can use star, no problem. And but this is the most standard notation. In groups, we usually use G star, G plus, G into. If it's multiplication, you into. If it's somehow related to addition, you might use plus. Or if it's very general, you might write G star. But here, most of the time, you'll write it as R plus and dot or R plus and this cross. Yeah, but those are just names and notation. It can actually be addition operation defined in some way. So once we have this definition, we can look at some examples. The basic example is here again integers. So actually, integers are the model for this ring structure. So the set of all integers and the operations plus is integer addition, normal addition that we know, and multiplication is simply normal multiplication. We already saw in the group part that Z plus is an abelian group. And you can verify the other properties. For integer, it is these are just properties we know. We don't usually write the proof for this. The distributivity holds for integers and multiplication is commutative associative. Identity element is the integer one. So this is a ring, set of integers under addition and multiplication. And you can notice that Z with multiplication is not a group. So multiplication doesn't have to be a group. It's not a requirement. Then we have the set of rational numbers. Again, addition and multiplication are standard. Here again, Q plus is an abelian group, and if you exclude 0, Q and its multiplication is also an abelian group. but that's not required for a ring. And distributivity holds. So this is also a ring. Similarly, R, set of all real numbers. C, set of all complex numbers. These are all rings under addition and multiplication defined naturally as we do in school. Then I had in one of the lectures given an example of a group called Gaussian integers. That is also a ring. Z of I defined as A plus IB, where A and B are integers, and I is the complex number, square root of minus 1. Here, if you add A plus IB plus C plus ID, you'll get A plus C plus I into B plus D. And if A plus IB is in Z of I, that means A and B are integers. And C plus ID is in Z of I means C and D are integers. Then A plus C is an integer and B plus D is an integer. So you get a number of the form A plus IB where A and B are integers. So this addition is closed. We can, I'll leave it to you. If you have doubts, you can verify yourself. But you can verify that Z of I is an abelian group under addition. Multiplication is again A plus IB into C plus ID will give you AC minus BD plus I into AD plus BC. And if ABCD are all integers, then AC minus BD and AD plus BC are also integers. So this is also closed. And 1 you can write it as 1 plus 0I, where 1 and 0 are integers. So that one identity element is there for multiplication. Multiplication is associative. That again, you can write three different numbers and verify it. It's not difficult to do. It's also commutative and similar to this is a subset of complex numbers and distributivity holds in complex numbers. So here also distributivity, associativity, everything holds. So this Z of I is also a ring under complex number addition and complex number multiplication. In fact, the set of complex numbers is also a ring, and this is a subset of that. So similar to how a group can have a subgroup, this would be a subring. I'll define that later. But subgroups were a very important concept or topic in group theory. Actually, we didn't get that far, but there are theorems that are very useful related to subgroups. Um, it says that the order of a subgroup always has to divide the order of the group itself. And if you have a homomorphism, uh, then the cosets, there is a homomorphism, there is an isomorphism between the image of the homomorphism and the cosets of the kernel, which is a subgroup. Similar, a lot of things related to subgroups are there. Later on in group theory, we couldn't get to that point. We'll try if we have time left in the end. But in rings, this subring concept is not that interesting and it's not that important. So subring is not doesn't give you too much other than what you get as a subgroup. So here you see that the ring is also a group under addition, right? So it kind of you already have if you have a subring that then that is also a subgroup under addition, and most of the interesting things happen within that subgroup itself, subgroup concept. That is with one operation. Yes, there are two operations. That will depend on the application where you're using it. So this is more like a tool, right? For example, even in calculus, when you learn triple integrals or any integral and all, it's mostly a tool to find out surface area or volume when you use it in physics. And if you use it in statistics, it is a tool to find averages. The math itself, uh, it's not that easy to say. It will depend on the field where you're using it. Groups are sometimes used in chemistry to, yeah, it's more of the, yeah, structure, geometrical structure, wherever it is there they might use groups. And we saw some Heisenberg groups and all, right? Yeah. So, and Pauli groups. But those I don't know whether they can be used as rings or not. But mostly from what I have observed, I don't know, right? Specific fields other than coding theory, I don't know. But in chemistry, I think they are more interested in the group structure and the symmetry that you get instead of the rings. So this is a very basic introduction that I gave to groups, and a lot of the fields uh, connected with the geometry and the symmetry of the Symmetries are what are important. So those kind of things, the ring structure is not necessary, I think. The group structure is enough. No, it's multiplication distributes over addition. At the property that I written. No, 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 no. You say the multiplication is distributed addition in this case. Yeah, multiplication in the left hand side, it's defined on the sum of two things, right? But on the right, on the left hand side. But on the right hand side, it's distributed to both A and B. So you say multiplication distributes over addition. Then you write C into B plus, and that is not required. No, see, you can't interchange that because the properties of addition and multiplication are different. They are not both groups. The inverse does not exist for multiplication. So you don't need distributivity for both in both ways. You need only multiplication distributivity over addition. You would simply replace, you would simply interchange plus and into in this. So you would write A into B plus C is equal to A into C plus B into C. You will see that in uh, in Boolean algebra, this type of thing holds, I think, right? No, not in general. Yes, it's not true there. Yeah, it's true in Boolean algebra. So the and gate, if you think of this as and or operation, then this is true. Yes, yes, yes. Yeah. The addition is the one with the most structure here. So it's an abelian group. For the multiplication, you don't need inverses. In case you have two operations which have everything, usually that won't happen because zero won't have an inverse. Um, unless in the trivial case where zero and one are the same, it doesn't really work out that way. So excluding zero, if the set is abelian with multiplication also, then that would be a field. Anyway, we'll come to fields later. For this ring part, you understood, right? For plus, it should be an abelian group. For multiplication, operation has to be commutative, associative. You should have a one. At least in our definition, it should be like this. Then the yeah one you can't forget about the distributivity also. So that is also an important part of this ring ring definition. So plus and into distributes over plus. Okay. Then Consider the set A is equal to A plus B by 2 where A and B are integers. Is this a ring? Uh, addition and multiplication. No, if A and B are integers, then you will get an what you will get. All integers are also real numbers. No? Oh, Z is a subset of rational numbers, which is a subset of real numbers, which is a subset of complex numbers. Why each of them is a subset of each other. So every integer is a real number, but every real number need not be an integer. When you're checking, you have to check whether A plus B by 2 added to another C plus D by 2, whether it is of the form A plus B by 2 for A and B integers. So if one of the numbers A plus B is B A plus B by 2, where A and B are integers, and another number is C plus D by 2, where C and D are integers, then you can write this as A plus C plus B plus D by 2, where A plus C is an integer and B plus D is an integer. So this number will also belong to the set A. Yes, yes, it is a collection of elements of that form, where A and A plus B by 2. No, no, that's not the operation. You can write C 0 plus 0 by 2, which is 0, is the identity. And you can simply write minus A minus B by 2, because minus A and minus B are also integers. Then you add A plus B by 2 plus minus A minus B by 2 is 0. So, and associativity will directly come from um, rational numbers, because a set of all numbers of the form A plus B by 2 is a subset of rational numbers. So, with respect to addition, this is an abelian group. Then we have to check multiplication. If you multiply A plus B by 2 and C plus D by 2, what is this? Yes, associativity and all is fine because they directly come from rational numbers. Yes, that has to be verified. Can we write? You'll have to. Yeah, but BD by 2, we don't know if it's an integer. And if it's not an integer, AD plus BC plus BD by 2 won't be an integer. So if we take a simple example with B is equal to D is equal to 1 and we set A and C to be 0, that if we take the numbers half and half, half is of the form it is 0 plus 1 by 2 and its product is 1 by 4 and you can never write this as A plus B by 2 for any integer A and B. Yeah, because if suppose A 1 over 4 was of the form A plus B by 2 for some integers A and B, then that would mean half is equal to 2A plus B. Should mean B is equal to, this will be 1 minus 4A by 2. But 1 minus 4A by 2 is not an integer for any value of A or any integer A. 1 minus 4A by 2 is not an integer because 4A is an even number. 1 minus 4A will always be an odd number. So 1 minus 4A by 2 will always be a fraction. So it cannot be an integer. Therefore, 1 by 4 cannot be written in the form A plus B by 2 for any integers A and B. But half belongs to the set A. So closure is violated by this multiplication operation. So this is not a ring. So yes, I said that in the beginning, right? That is baked into the definition of binary operation. Maybe I'll write this as two with two binary operations. So what some books do is they will include that closure as a property in the properties that have to be followed. I listed only three, right? They'll include closure as the first property, maybe. Um, but what we have done, as is done in many textbooks, is we have defined a binary operation to be a closed operation from ordered pairs to the set. That is from R cross R to R. And in the definition of binary operation itself, we have said that it has to be closed. Yeah. Yes. Yes. So we define binary operation that way, that it is closed. Not all books do that. In the books where binary operation doesn't include closure, they will have to include it everywhere. Uh, they'll have to include closure in the definition of groups, rings, fields, everywhere. Instead of doing that, we have simply said A binary operation is a closed operation. Again, it's more stylistic choice. It depends on you what the author wants to do. Similar to how this ring we have uh, included commutativity. So this is it actually comes under commutative algebra, uh, where the structures are all commutative. And we also included an identity element. It's not strictly necessary. You can work with rings without that also, without that requirement. But it's our choice here. Then we define this subring. Let R be a ring. A subset S of R is a subring if it is if R plus is a subgroup. Sorry, if S plus is a subgroup of R plus, multiplication is closed and S contains 1. So here, since you have two operations, when we define subring, we want it to be a subgroup with respect to the first operation. Then with respect to the second operation, we just need closure and it should contain 1. Uh, no, at least not according to our definition, but uh, I'm not sure if it is defined differently in different ways, different places. Not really. I mean, the since it's the same multiplication. Sorry, I have someone at the door. I'll come back in a minute. Hello. Okay. Anyway, actually, we don't use this subring stuff anywhere, so it's not important. You should check a textbook, perhaps. Uh, this is from some lecture notes. So, yeah. Here for rings, the more important concept is the concept of ideal. The place of subgroups is taken by ideals for rings. No, the ideals are for rings. There again, for fields, subfields are what are more important. Subfield of a field. So there, the ideal concept is not important anymore. For rings, the ideal is important. For groups, the subgroup. Yeah. Next, like I said, it is possible to define rings without asking for multiplication to be commutative. Um an example would be the matrices with addition and multiplication. So according to our definition, since we want multiplication to be commutative, matrix rings are not considered. So we won't deal with matrix rings. But you could define that, right? Because matrices also are interesting stuff, and many cases you might want to deal with multiplication there. And again, the if you take the set 2z, that is all integer multiples of 2, that is that would be a subring of the set of the ring of integers. That would, but not under this definition. See, under this definition, the set 2z doesn't have one, right? So it can't be a ring, even though rest of the properties are satisfied. So if the definition did not require one to be included, then 2z, 3z, all these would also be rings. So now, since we have defined one has to be in the ring and subring, uh, 2z, 3z are all simply subgroups of z under addition, but they are not subrings of z under addition and multiplication. So if you had to deal with structures like 2z or 3z and you wanted to deal with the multiplication aspect of it also, then you would have to remove the condition that one has to be in the ring. Yeah, so those are examples where the ring is not commutative, which is matrix ring, and a ring which does not have identity, which is 2z. But in whatever we will be dealing with, we will always consider commutative rings with identity as simply rings. So for the rest of the lectures, I won't When I say ring, you should automatically understand that I am talking about commutative rings with identity. Actually, the most trivial ring you could have, we'll go back to examples. Okay, first I'll give examples of subrings would simply be Z, Q, R, Z of I are all subrings of the ring of complex numbers. Okay, then let's go back to the examples of rings. We are at 4, then we'll 5, 6. The most simple ring is the ring with 0. See, in this ring, 1 equals 0. This is a ring. This is called the 0 ring. No problem with that, right? There's just one element. So 0 plus 0 is just 0, and 0 into 0 is 0. And the definition for multiplicative and additive identity is satisfied if there is only 0 in it. Yeah. So everything is satisfied. So you are allowed to have a ring in which, so the definition doesn't say that the multiplicative identity has to be different from the additive identity. So of course it is in the zero ring it is the case that both are equal, but you can define things, define rings where both multiplicative and additive identity are same, uh, and you can check if having that condition um, and the other conditions whether that makes the ring to collapse into the zero ring. If you set the additive and multiplicative identity to be the same, what will happen? That you can try it out as some interesting exercise. Can you have a ring that is not the zero ring, in which both the multiplicative and additive identity are the same? So now CZ is set of all multiples of 3, integer multiples of 3. Consider the quotient group. Actually, I have not defined what a quotient group is. But in this case, just think of it as the equivalence classes of the addition, mod 3 addition. So here, unlike Zn, Zn was 0, 1 up to n minus 1. And there actually we were not dealing with the equivalence classes. We were dealing with the actual numbers, integers 0, 1, 2 up to n minus 1. Here we are dealing with, in that sense, um, for example, you had, if you consider Z3, which is 0, 1, 2, 3 is not a member of Z3. Even, okay, where you are dealing with mod 3 addition, 3 does not belong to Z3. But here Z mod 3Z, you have 0 bar, 1 bar, 2 bar, the equivalence classes. 3 bar belongs to Z mod 3Z because 3 bar is equal to 0 bar. The equivalence class of 0 is the equivalence class of 3. So that's actually the difference between Zn and Z mod 3Z. In Zn, you are dealing with the actual numbers. Only the operation is defined modulo 3. But in Z mod 3Z, you are dealing with the equivalence class of numbers. So 0 bar is actually the set of all multiples of 3 here. It is this set. That is what 0 bar is. 0 is just a number within the set that you use to represent this equivalence, this set. So this same set can be written as minus 3 bar. It can also be written as 3 bar. Just you can pick any element within the set to represent it. But here 0 is the actual number 0, simply the integer 0. Now they are the equivalence classes. Yes, it is a set of sets. Set of all equivalence classes. Where the equivalence relationship is uh, congruency modulo 3. Yeah. Yes. This is in for addition, 0 bar is the identity. It is the additive identity. Because of the way we define this, we define the equivalence class of A plus equivalence class of B to be equal to the equivalence class of A plus B. And the equivalence class of A into equivalence class of B is equal to the equivalence class of A into B. Infinite group, you can't really draw it, right? And how will you draw it? There are infinite elements, so you can't really draw it. And you can't really store it also in a computer or anywhere. You can theory, the table format doesn't give you anything. Yes, yes. You can write, um but again, the table is for groups, and under multiplication, this is not really a group. So you can draw for the addition part. Yeah, that's no problem. The element is actually the number of elements has to be finite. What the element is, how it is defined, that is of no consequence to. Yeah, that is what the abstraction is useful for. So you can simply here again, uh, we simply talk about if you have two elements, how it is defined. But what A bar means and what B bar means are completely up to you. What matters is only how it is defined and if it has the properties that it needs. So there's no problem defining the elements to be sets of infinite length. That doesn't have anything to do with the finiteness of the ring or group itself. So here, what um, at the end of the day, um, actually you will have to check whether these are well-defined operations first. That is, here 0 bar is equal to 3 bar, right? And 1 bar is equal to 4 bar. So if you take 0 bar into 1 bar, that is 0 into 1 whole bar, which is 0 bar. You take 1 bar into, so 4 bar is actually 1 bar. That is 4 bar, which is equal to 1 bar. Sorry, that's not what I meant. If you write 3 bar into 4 bar, that would be 12 bar, which would be 0 bar. So the product at the end, product equivalence class, doesn't really depend on the representative you picked. So whether you represent this class using 0 bar or using the element 3, and whether you represent the equivalence class of 1 using 4, it shouldn't matter. The product of two equivalence classes should be the same equivalence class, regardless of the representative element that you pick. Only then this operation is actually well defined. But it turns out that if you define this operation as simply um, a plus b is actually mod 3, then it will be the case that regardless of the representative, these will be well defined operations. Usually we don't write this mod 3 part here. We simply write it like this. When it comes to addition, if you want to write the table, this is the 0 bar 1 bar 2 bar, 0 bar 1 bar 2 bar, 2 bar, this is 0 bar, this is 1 bar. Uh, Multiplication, it will be 0 bar times 1 bar is 0 bar. So it's closed. You can check the multiplicative identity is 1 bar. Uh, the associative multiplication is commutative. All the properties hold. So this is actually a ring. Now the condition here was that uh, now instead of this 3, if you take some other number also, this all the properties will be the same. So for n greater than 0, n is an integer. Z mod nz is a ring, and there are exactly n elements. So here one thing you have to note is that this is not a subring of the complex numbers. So these are actually equivalence classes, right? Uh, not the element themselves. The operation is not exactly the same. So it's a different, even the operation is different. So here we had Z, Q, R are all subrings of C. So this is one example where, and even A plus B by 2 that we saw. Uh, okay, it did not turn out to be a subring, but we are looking at only subset of C. But this is one ring which is not a subring of complex numbers. Another such one would be the uh, considering functions. R is a set of all functions from real numbers to real numbers, such that f is a continuous function. You can induce a ring structure by defining addition in this way. For two functions fg in R, f plus g of f plus g is a function such that f plus g of a is f of a plus g of a. Multiplication is also pointwise. F times g of a is f of a into g of a. So the sum function is simply sum of the individual functions at each point. The product function is has the value of the product of the two functions at each point. Now, one thing you have to first verify that you do in calculus is that sum of two continuous functions is pointwise. If you define it be sum, then it is also a continuous function. from real numbers to real numbers, and the product of two continuous functions defined in this pointwise way is also a continuous function. That is part of calculus. We'll assume that it is true. Then addition is commutative because addition is commutative here. Addition is commutative in real numbers. So f of a plus g of a is equal to g of a plus f of a. No, they are functions. A function is defined for all points in its domain. Yes, it is the ring of the function. A function itself is from one set to another set. It is a mapping from one set to another set. So the way you define a function is by giving the value of the function at each point in its domain. So that gives you the mapping of the function itself. So if I give a number a in the domain, what is the output? F of a. That is what decides the function f. They are saying if the addition of two functions is another function, and what is the value of that function at any point a in the domain? That will simply be the sum of the value of the two separate functions that you are adding, evaluated at that point. Yeah. So if you had one f like this and g was like this, then suppose this was 1 and this was the absolute value function, mod x. And f plus g would be like this. And fg would simply be f itself here because g is constant function 1. Oh, it is continuous. It's not differentiable. It is equal to 0 at 0. Yeah, continuity, we'll have to check limit of f of x as x approaches a is equal to f of a. Is that true? That we'll have to check. For mod function, it is. Yeah. Yes. 0 plus uh, modulus is simply plus 0 and 0 minus modulus is simply minus 0. But minus 0 is same as plus 0. Yeah. Another way is from the graph, if you can draw it without raising your pen from the plane in which you are drawing the function, then it's continuous. So you can continuously draw the graph in one stroke. So these are closed. The the closure is you'll have to use calculus. That's the sum formula. That's all. Because f plus g of a is limit is f of a plus g of a. Limit of f plus g of a would be equal to limit of f of a plus g of a, which is simply or limit of f plus g of x is equal to limit of f of x plus g of x. Because f plus g of x is defined to be f of x plus g of x. But by the sum rule, limit of f of x plus g of x is equal to limit of f of x plus limit of g of x. And limit of f of x is simply, if it extends to a plus, that's simply f of limit, that's simply equal to f of a, because f is continuous, whether it is a plus or a minus. Similarly, whether it is a plus or a minus, limit of g of x is g of a. So it is closed and the additive identity is zero, is the zero function. That is defined as for any number maps it to zero. And minus f is a function defined to be minus f of a is equal to minus of f of a. That's the inverse of f. The multiplicative identity is the function that maps every number to 1. And you can verify distributivity associated to everything. This is a ring. Are you convinced, or is there any property that you are not convinced with? Yeah, okay. Then we saw that, um, suppose, for example, you take the ring of integers, the number 1 has a multiplicative inverse, and the number minus 1 also has a multiplicative inverse. And we saw in the set of rational numbers, other than 0, all the elements have multiplicative inverses. So we give a name to numbers that have a multiplicative inverse in a ring. Let R be a ring, an element A in R is called a unit. It's a unit and not unity. Unity is the number 1, the multiplication, the identity element that you usually call unity. Here it is simply unit if it has a multiplicative inverse. We always have, if R is a ring, then 1 is a unit, since 1 dot 1 is equal to 1. So the units of, what are the units in Z? Yes, 1 and minus 1 are the units. And what are units in Q? Yeah, if A by B is an element, B by A is its multiplicative inverse, and A by B times B by A is equal to 1. As long as A by B is not equal to 0, because 1 by 0 is not a rational number. So other than 0, everything is a unit. And note that 0 is the uh, additive identity here. So other than the additive identity, all elements are the unit. So that type of ring is called a field. So a field is a ring R in which every non-zero element is a unit. So in this definition, we are saying every non-zero element is a unit. But if you want to define it this way, uh, the identity element and the identity element of addition and multiplication have to be different. That's something which is implicit to this definition. So we can't have the zero field. We can have zero ring in which the zero was same as one, but you can't have the zero field. Smallest field would be it must contain 0 and 1, which is the binary field. Yeah, yeah. Uh, yes, yes. Ah, for multiplication, you have to remove the zero element. Yes, and the distributive property should also hold. Yeah, so it just has one more extra condition than our ring, but that makes a huge difference. If you look at the structure of rings, and if you look at the structure of fields and all, the existence of inverse for all non-zero elements. That's actually a very large ask. It is asking for a lot. So that's why we study these two as a separate. We don't simply study fields as a type of ring because that property makes a lot of changes. That's why we study fields as a separate entity. Example is Q, R, and C. Z fails to be a field. So Z is actually truly a model for ring structure, but it is not a field. Were you saying something? Galois fields are finite fields. QRC are not Galois fields. Yes. Galois did a lot of research on this topic. You can say he's the father of finite fields, kind of. So it's named finite fields are named after him. Yeah. QRC are not Galois fields. How is ah yeah. Um, in application, right? You usually cryptography, coding theory, communication everywhere. You only come across you in coding theory and cryptography mostly. Communication sometimes communication you deal with real numbers also. But in cryptography, I'm not sure. But in coding theory, at least, you only deal with finite fields. You usually don't deal with real numbers. Uh, uh, in classical coding theory, modern coding theory is a bit different. In classical coding theory, you deal with only finite field elements. There, the field will be referred to as UF of some number and UF of some. Yeah. So that means it's a finite field of size n. And it turns out that finite fields, if they can have only particular sizes, and all finite fields of the same size are isomorphic in the sense of fields. So we saw homomorphism in groups. Homomorphism did not require the homomorphism function phi to be a bijective. It was possible to have a function that was not onto, and it was also possible to have a many to one function as a homomorphism. But if you restrict it to a bijective function, that is, it must be onto and one to one, then such type of homomorphism is called an isomorphism. And once you have an isomorphism, what happens if that it's a structure, it's not just the bijectiveness, right? It's also the structure preservation. So if you add two numbers in the domain and then take the function, that is same as taking the function value of the two domain elements and then adding them in the codomain. So it was preserving the additional structure. Uh, when it comes to fields, you have two such things, so it will preserve both addition and multiplication. And when that happens, essentially there is no difference between the groups of the field. right? If you have A, B, C, D is one of them, and the A, B, C, D is the other group, and there is a mapping, one-to-one mapping like this. And also, if A plus A is equal to, let's say, if A plus B is equal to C here, then A plus B is equal to C in the other group. Then what is the difference between these two groups other than their names? Is there any difference, mathematically speaking? Yes, if you have an isomorphism, then is there any true mathematical difference between the two groups? Not really, no, right? There is no difference. Uh, Here, if you add two numbers and you get C, then you could have added the image of those two numbers and got the image of C. So instead of doing the operation here and getting C, you could have added these two, got C here, and then went back using the bijection. It would come to the same thing, right? You can get the result of an operation by doing the operation on either of the fields and simply taking the moving using the mapping. And if you have a subgroup here, suppose the subgroup contains only BCD, then you have a subgroup containing BCD here. That will be a BCD is a subgroup in the domain, then capital B, capital B, C, capital D will be a subgroup in the codomain, and vice versa, since it's a bijection. Opposite also holds. If capital B, capital C, capital D are a subgroup of the range, then BCD is a subgroup of exact whatever properties. If the order of B is something, then the order of capital B will be the same thing. So whatever properties you can find in this group, everything will be the same in this group, except that the name is different. In this group, this element is called A. In this group, it is called capital A. So, mathematically speaking, that is the case. So you can think of it as if you add four apples, uh, you take four apples, and if you take four oranges, mathematically there would just be four objects, four similar objects. And then if you took two more apples, you would have six apples. But correspondingly, if you took two more oranges, you would have four plus two, six oranges. So whether you're talking about apples or talking about oranges, mathematically you're talking about four objects of the same kind. So here, instead of the same kind, there are four objects A, B, C, D with names A, B, C, D, but they are exactly the same as four other objects with names capital A, capital B, capital C, capital D. Mathematically speaking, there is no difference between them. So for a mathematician, both groups are the same. So in a if they have all the structures are the same, if there is an isomorphism. So what can happen is, like we saw in um, groups. Yesterday, last week or sometime, I did a problem where we were showing that all groups of size less than or equal to 5 are abelian. When we went to four groups of size 4, The group could have either been cyclic group, EA, A square, A cube, or it could have been a not non-cyclic group, EAB, AB. These were two different structures that were possible for uh, a group of size 4. If you said, then it had to be one of the two, but you had two different possibilities just for size 4. That is true for groups. But when you come to finite fields, there is only one structure. It is of this structure. And all finite fields of the same size are isomorphic to each other. There's some bijective mapping that preserves the operation when you move from one to the other. Yes, as long as they are both finite and of the same size, then they'll be isomorphic to each other. So you can simply deal with an easy to understand group of easy to understand finite field. Mostly we will be dealing with finite fields defined using polynomials and modulo arithmetic in polynomials. Then, um, if you were able to come up with a field in some other way without using the polynomial, that will be isomorphic to that polynomial field. So you can simply do all your work in the polynomial field. And then whenever you want to go back to your original framework, simply take the inverse of whatever isomorphism is there. Another example of this type of thing is in graphs. So suppose you have a graph with three vertices in which all the vertices are connected to each other. Now, whether you name this node A, this node B, or this node C, or you name this node A, this node B, and this node C, or you name this A, this B, and this C. At the end of the day, you have the same graph, right? Only the naming changed. You could always rename this B to A, and this C to B, and this A to C. That's still the same graph structure. Only the node names have changed. The property of the graph that it is connected is the same, right? It won't change by changing the node name. Property of the graph that it is a cycle, that won't change by changing the name of the nodes. So structurally, these two graphs are the same graph. But when you write it when you name them, when you give labels to the vertices, that will again, when you simply write down the vertices, you can't really tell which of these it is. Only when you draw it like this by giving it a particular orientation, then these names will be important. But the structure of the graph is same in both the graphs. The property will not depend on the names of these nodes, properties of the graph. So in that sense, these two will be isomorphic graphs. And most of the time, when you're talking about the coloring of a graph or the connectedness of a graph, whether it's a bipartite graph or not, all those properties of the graphs will simply depend on the graph structure, not on the labels that you give to the vertices. Okay, now similar to Z mod, we had this example of Z mod 3Z, and you can observe that in this um 1 bar times 1 bar was 1 bar, and 2 bar times 2 bar was 2 bar. So 2 bar inverse is 2 bar, 1 bar inverse is 1 bar. I'll write to the power minus 1 when it is the multiplicative inverse. I'll write minus like this when it's the additive inverse. So here, other than the zero element, which is the 1 bar and 2 bar, have a multiplicative inverse, right? So other than the zero element, all the elements have a multiplicative inverse. So this is a field, Z mod 3Z. No, it is the inverse. That's why you asked, right, whether we are talking about it as an element or we are not concerned with the what 1 bar means at all. We are only concerned with the operation. Yeah. So I already fully. We only use the concept of this 3Z and then modulo 3 addition, all that to understand, to help us better write the operations here. But if I told you nothing and simply gave you the operation values, if I gave you this and this, that would just define the uh, ring and its operations. And then if I told you how to, I also have to describe the distributive property. But then verifying all that, okay, that distributivity is no problem. So as long as I tell you the result of the multiplication between any two of the elements, and the result of addition of any two elements, that is actually enough. So even someone who does not know anything about modular arithmetic can understand that, can verify that this is a ring. And the inverse is simply an element such that if you multiply it with its inverse, you get the identity. And in this case, identity is 1 bar. So in case of 1 bar, if you multiply with 1 bar, you get 1 bar. So that is the inverse of 1 bar. Here, if you multiply 2 bar with 2 bar, you get 1 bar. So 2 bar is the inverse of 2 bar. There's nothing to do with what 2 bar actually is. Then what about for other integers? What about z mod 2z? Which is 0 bar and 1 bar. 0 bar is the set of all even numbers and 1 bar is the set of all odd numbers. Here is a group, it is a ring also, and only non-zero element is 1 bar, which is its own inverse. So this is also a field. We already said that Z mod nz is a ring for all n. So now we are just checking if they're a field for all n, or if not, which of the n's, which of the integer n will give you a field. Is this a field? I already said that they're all rings, so they're all groups also. Yeah. We only have to check if all the non-zero elements are units, that is, they have multiplicative inverse. Do all the elements here, non-zero elements, have a multiplicative inverse? Which one will give you 1 bar? You have to take with all elements and see if any of them gives you 1 bar, that's all. And none of them give you 1 bar, so 2 bar doesn't have any inverse, so it's not a field, that's all. That's why you have to just know the definition and use it. Um, Inverse of A is some element B such that AB is equal to the identity E. Inverse of 2 bar is some element, some B bar such that the product is the identity. Here, multiplicative identity is 1 bar. And you can see that 2 bar times any of the elements is not 1 bar. So 2 bar have no inverse. A ring is a field only if all its non-zero elements have an inverse. So 2 bar is not a zero, it's not the zero element, and 2 bar does not have an inverse. Z mod 4z is not a field. In fact, Z mod nz is a field if and only if n is a prime number. Why is that? Can you prove this? You have to prove two things. If n is composite, it is not a field. And if n is prime, it is a field. Yeah, you can't just say that, no. You can't just say that it will exist. You have to show how. You have to find a B for every A such that AB is one mod P, right? Use the preliminaries we had done um, when we are doing GCD. No, no. Yeah, you can't take two different elements like that, right? If I take any two random elements, they won't give me one. But if P is a prime, what are its divisors? So any other number will not uh, for any pick any class here. Pick some class A bar or X bar. Pick a representative which is pick A such that it is between 1 and n minus 1 and A bar is equal to X bar. You can always do that. See, this is simply notation for the equivalence class of X, and equivalence class of 1 will be the same as equivalence class of n plus 1. This will be the same as equivalence class of 2n plus 1, right? So when you if you go back to relations and see, the equivalence class of an element is the set of all elements X such that X is related to A. But so here in our case, the equivalence class of X A is set of all X such that X is related to A means X is congruent to A modulo N. That is X is equal to A plus NQ for some integer Q, right? So X was congruent to A mod N if and only if N divides X minus A. That is how we defined it. So n divides x minus a implies x minus a is n times q for some integer q. That's what we meant by the definition of division. So simply x is equal to a plus nq for some integer q, right? This is a set of all x such that um, x is equal to a plus nq. But then this is also the same as the equivalence law of a plus n, because if x is equal to a plus nq, then x is equal to a plus n plus n into q minus 1, right? You can write nq as n into q minus 1 plus 1, and you can write this as n into q minus 1 plus n into 1. You can write it as a plus n plus n into q minus 1. X minus a plus n is equal to n times q minus 1. So n divides x minus of a plus n. So this x is congruent to a plus n mod n also, but it is congruent to a mod n. So there is the same equivalence class. So you actually pick a representative element in this set. Any element in this set, you can write it as the equivalence class of that element. So here the equivalence class of 0 is minus n, 0, n, 2n, etc. But this is also equal to equivalence class of n. This is also equal to equivalence class of 2n. This is equal to equivalence class of minus n. Right? This 0 is just a placeholder, a representative to represent the set, the equivalence class. But the thing is, for an equivalence class in this set, you can always find some number that is between 0 and n minus 1, such that it is equivalent to that equivalence class. So for any number x, any integer, the equivalence class of x bar can be written as a bar for some integer a which is within these bounds, right? So once you pick a greater than or equal to 1 less than or equal to n minus 1, now what do you have? You have a is some number less than n, right? Now, so if a is greater than 1 also, for 1 we already have the inverse is 1. Or if it is greater than 1, a and n are relatively prime. Here we are showing if n is prime. If n is prime, a and n are relatively prime. the reason we chose a representative that is less than or equal to n minus 1 was so that this relatively prime thing holds. Because relatively primeness is uh, anyway, we know that all numbers less than p but greater than 1 are relatively prime to the prime number p. Now, the fact that we studied in the preliminary in the first lecture is that if two numbers are relatively prime, you can write as plus for some integers s and t, you can write as plus nt is equal to 1. Relatively prime means what? It means that GCD of a and n is equal to 1. And we know that the GCD of two numbers can always be written as a linear combination of the two numbers with integer coefficients. Since GCD is 1, we can always write as plus nt is equal to 1 for some integers n and t. But what does this mean? This means that as is equal to 1 minus nt is 1 plus n into minus t. As minus 1 is n times minus t. So n divides as minus 1. So as is congruent to 1 mod n. Or the class of as is congruent to the class of 1 mod n. But by definition of multiplication of equivalence classes, you can split as a equivalence class of a times equivalence class of s. Then there exists some s bar that is between that is greater than 1 and less than n. Thus that s bar prime is equal to s bar. S prime bar is equal to s bar. And this, but a, a bar times s prime bar is also equal to 1 bar. So s prime bar is the inverse of a bar. Was that okay? Yeah, so you can always find some integer s and t such that as plus nt is equal to 1 if a and n are relatively prime. Then as plus nt is equal to 1 means if you take mod n, as mod n is plus nt mod n is equal to 1 mod n, but nt mod n is 0 because it's a multiple of t. So as mod n is equal to 1 mod n. That means they are in the same equivalence class. Equivalence class of as is equal to equivalence. Only problem here is that this s can be an integer that is not within 0 and n minus 1, right? But we know that even if that is not the case, okay, actually that is not required. That is not required because s bar will always belong to z mod nz for any integer s. Yeah, you can always find some representative within 0 to n minus 1 for any equivalence class, and that will simply be the inverse of a bar. This is one type of proof. There are other proofs for the same thing. Another proof would be like this. Another proof would be if you know that now we have shown that Z mod LZ is a ring, but if you can show that it is an integral domain. So an integral domain is one in which the product of two numbers is zero only if one of them is zero, right? Is that okay? Yeah. For example, in integers, only if you multiply zero with some other integer, you will get zero. If you multiply two non-zero integers, you can't get zero. But in matrices, it is possible to get a zero matrix by multiplying two non-zero matrices. Yeah, for example, you can simply multiply um, yeah. So here you would get zero. This would be zero, zero, zero. So the set of matrices, even if you had the matrix ring that I said, here we require commutativity of multiplication. But if we don't add that as a condition, then uh, you would have the ring of matrices. But in that case, it's not an integral domain, even though it is a ring. So an integral domain is a ring such that product of two entries, the product means the second operation, multiplication of two entries is zero only if one or both entries are zero. So if you know that, uh, and we can show that Z mod nz is an integral domain when n is prime. So once you know that, then you can, from there also you can show that it is a field. Of course, showing that is also something that's non-trivial. You will have to write a proof for that. But suppose you have studied integral domains and you know that uh, when n is prime, Z mod nz is an integral domain. Suppose you know that fact. Then what you can do is you take that non-zero element. So a bar was all non-zero elements uh, must have a inverse. So you don't need to consider zero. Suppose you take a non-zero number, then you have this set, the set of one, two, etc., n minus one whole bar. Then you multiply each element by this a bar. So you get a bar into one bar, a bar into two bar, etc., a bar into n minus one whole bar. Now what has happened? Now you have, so since a bar is an element of this set, a bar is an element of this set. So the product of a bar with any of its elements is also within that set. Right? We needed multiplication to be closed. Yes. Yes. So here there are some small points. The first small point is multiplication is closed when you include the zero also. So, but that's one point where the fact that it is an integral, it is not an integral. So it is an integral domain comes into picture. So when you multiply a bar with any of these, you won't get zero bar. You will get something within this set itself, right? Because a bar is not 0 bar and none of these is 0 bar. So the product of a bar with any of these won't give you 0. So it must be within this set, a bar times any of the element here. The second thing is that a bar times any b bar cannot be equal to a bar times c bar. So they must all be distinct. Again, that for the reason for that is you could write it as a bar b bar minus a bar c bar is equal to 0 bar by adding the additive inverse of a bar c bar. Then using the distributive property, you can write this as a bar into b bar minus c bar is equal to 0 bar, right? Then, since it's an integral domain and a bar is not 0, the only way b bar minus c bar can be 0 is if b bar minus c bar is equal to 0 bar, since it's an integral domain. Otherwise, this need not be true. Then that would mean that b bar is equal to c bar. So if you have a bar times b bar is equal to a bar times c bar, then b bar must be c bar. Or in the opposite way, if a b bar is not equal to c bar, then a bar times b bar is not equal to a bar times c bar. So each of these is a distinct element. Only then it will become a reordering of this set at most. So these two are equal. That means that for some b bar in the first set, a bar times b bar must be equal to 1 bar. Because one of these elements has to be 1 bar, right? Since it's just a reordering. So you found the inverse. B bar is the inverse of A bar. That's one way you can prove if you know that Z mod n is prime. Which would, if you know that when n is prime, Z mod nz is an integral domain. Otherwise, you can't use that fact. Okay, that is only one side of this. Um if n is prime, Z mod nz is a field. So what about Z mod nz is a field means that n is prime. That is, if n is not prime, Z mod nz is not a field. Can you prove that? It's very simple. Eh, but that you can't simply say that. No? You have to show it. So if n is, you have to show, but here you are showing it is not, you are showing the negative of it. So you can show, give a counter example. Yeah, n is composite means it can be written as AB for some numbers a and b which are between 1 and n. Then n bar, the class of a n bar is AB whole bar is equal to a bar into b bar. But n bar is equal to 0 bar. So a bar into b bar is equal to 0 bar. Thus, a bar and b bar do not have any inverse. Because if, see, we are saying that a b is between 1 and n. So a bar and b bar are not equal to 0 bar. Right? For some number between 1 and n, the recurrence class cannot be equal to 0 bar. Then suppose A bar had an inverse. You could multiply on the left by A bar. What would you get? You would get B bar is equal to 0 bar, which is not possible. Suppose B bar had an inverse. Then B bar inverse would be 0 bar, B bar inverse should be 0 bar. But A bar into B bar inverse is nothing but A bar into 1 bar, which is A bar. Which would mean that A bar was 0 bar. That's also not possible because A and B are both between 1 and minus 1 and n. So we have shown two elements. We have shown even one is enough. But we have shown two elements that do not have an inverse. So Z mod nz cannot be a field. Is that fine? Okay, I didn't see the time, but it's already long past 9 o'clock. So we'll stop here.